Seems to be that time of year for people to be talking about proving trig identities. I've seen several of these on various math subreddits, and also somebody I'm working with for tutoring pre-calc. We've done some talk about trig identities recently, and so I thought it would be a good idea just to show two examples, one each, that illustrates a couple of overall strategies for how to get these things done. Okay, so the first strategy, if you are asked to prove a particular trigonometric identity, is best for when the trigonometric identity is of the form some big messy thing on, say, the left side of the identity is equal to some nice, tidy, simple thing on the right side of the identity. Now, in that case, what you can do is just start with the messy thing and just evolve it, revise it, revise it, revise it using trig definitions or other identities, cancellations, things like that, until suddenly, boom, the simple thing pops out. And then you have a linear progression from the original messy expression to something a little bit better, something a little bit better, and after several steps, maybe more, finally you land on this other simple thing, and now you have, if all of your steps have been done correctly and you've not destroyed the equal sign in the process, since this is equal to this is equal to this is equal to this, you have equality from the start of your process to the end of your process. Okay, so here is an example. We're going to prove that the sine of a plus b over cosine A cosine B is equal to tangent of A plus tangent of B. So the left-hand side is a little bit messier. It's got a quotient. It's got A and B wrapped up inside of a single sine function. What are we going to do about that? Okay. Well, the first thing we ought to do is unlock this sine of A plus B so that we're only dealing with trig functions of A and trig functions of B as their own little bits to this whole puzzle. So we're going to open the bedding with this trigonometric identity, which hopefully is familiar to you if you're proving trig identities. The sine of A plus B is sine A cosine B plus sine B cosine A. So we're going to get this started by beginning with the expression that was on the left, right? We're starting with the messy thing on the left, and we're opening our bedding with the expansion of the numerator according to that very familiar trigonometric identity. Now we have two terms in the numerator being added, and that's over a single denominator, so we can then separate that fraction across the plus sign. And here now I've highlighted some things to focus on in each of those individual expressions, because now you can see from the cosine b's in the numerator and denominator of the left term, and the cosine a's of the numerator and denominator of the right term, those are ready to cancel. And now we're just back to the regular old definition of tangent, which is sine over cosine. And so now we've generated a string of equalities that started with sine of A plus B over cosine of A cosine B, which was equal to this mess, which was equal to this mess, which was equal to this mess, and finally is equal to tangent of A plus tangent of B. That's the transitive property of equality in big time action. All of these things are equal, and so certainly the first expression is equal to the last expression. So we started with the messy thing, revised it, revised it, revised it, boom, the simpler right-hand side thing popped out. We're done. Okay, the other strategy that usually comes into play for these things is where you have a trig identity that might be a messy thing equals another messy thing. And so it's not immediately obvious, like we should take the one on the left and evolve it to the one on the right, or start with the right and evolve it step by step back to the one on the left. Maybe we've got to just evolve everything all together. And that's going to be the key here. So if it's some messy thing equals some other messy thing, don't start with one and aim for the other. Just rebuild the entire structure, the entire equality, one step at a time, where you're adapting and tinkering with each side of the equation and maybe bringing them to some happy middle ground where you can see that they're both equal to the same thing. Okay, so we start with the original, some messy thing is equal to another messy thing. We revise the left-hand side and we revise the right-hand side. As long as you're revising properly, canceling, multiplying up and down by the same thing, factoring properly, as long as the algebra holds up, these equalities should still be intact. We keep that going through 2 steps, 3 steps, 28 steps, whatever it takes. And finally, you come to a point where you say, well, wait a minute, I now see exactly the same thing on the left side and the right side of my revised expression. And that locks it in. Because again, as long as the algebra is done correctly, a proper revision of the left-hand side or the proper revision of the right-hand side doesn't break the equality. And so the top expression, which was the original, is equivalent to the next expression, means it tells you exactly the same information. And that keeps up till you get to the bottom. Now the bottom, if you have something equals itself, so you got this thing on the left equals and exactly the same thing there, well, that's self-evident that something equals itself. But then instead of following the equivalence of statements from the top to the bottom, now you could march that equivalence from the bottom to the top, where you start with something that's evidently true because it's this thing equals itself, right? But then you're revising the 2 sides a little bit differently and eventually go uphill back to the original proposed identity. So those string of equivalences can flow downhill, but once you've established that locking in, you can then say that you would follow them uphill, and being able to do that shows that the top expression, the original offered trig identity, holds up, is proven. Okay, now in these processes, when in doubt, convert everything back to sines and cosines. If you don't like seeing cosecant, fine. Get rid of your cosecant, write it as 1 over sine. If you don't like secants, write it as 1 over cosine, and so on. Okay. The other thing to remember is you are the one in charge of all these expressions. Somebody handed it to you, but from that point on, you're in charge. If you want to do something to that expression, then do something to that expression. Just do it properly and correctly. Hopefully it's something that's going to help you out, but if it's not, you don't hurt anything. If I take an equation and multiply both sides by 18 over 3, I'm allowed to do that. Maybe it doesn't help, but I can because I'm in charge. And if I multiply both sides of an equality by the same constant, it's still the same expression fundamentally. Okay, try something. You don't need to see the entire evolution of the entire argument before you even begin. Just try something. Try a step, try another step. Even if you don't make it through, you'll have gained some intuition about things that don't work, and that itself is helpful. Okay, so here's an example of this type of identity where it's not really clear that we can get one of these things and revise it individually to produce the other one. So let's just evolve the entire expression altogether. Rule number 1, you don't like secants and tangents? Cool. Secant is 1 over cosine. So, and tangent is sine over cosine, right? So there we go. Let's throw out the secant, write it as 1 over cosine, throw out the tangent, write it as sine over cosine. Oh, now look, now we can combine those 2 terms on the left-hand side. Okay, now we've got 2 expressions which are nothing but sines and cosines, but still we're in the position where it's not obvious that this one's going to lead to this one. They both look equivalently yucky, right? So let's evolve both of them. Let's work on the entire expression, not just one side. What's the worst thing about this expression? Fractions, right? Now, how can we get rid of the denominator on this left-hand side? We can multiply it by cosine. But that also means we have to multiply the right-hand side by cosine. Okay, remember, you're in charge. If you look at this right-hand side and you say, man, I wish I could multiply that by 1 minus sine theta, you're allowed to. You can multiply it by 1 minus sine theta, but the cost is that you also have to multiply the other side by 1 minus sine theta. So let's agree that we would love to multiply the right side by cosine theta, sorry, the left side by cosine theta. We would love to multiply the right side by 1 minus sine theta. In all, we want to multiply both sides by both denominators. We could have done this one step at a time, but I'm just kind of blending it through. So we can see the cosines are going to cancel on the left side. We can see the 1 minus sine thetas in blue are going to cancel on the right-hand side. The point of this, I just recopied this for a fresh screen here. The point of this is that the fractions are gone. Okay, now, maybe we can multiply this left-hand side out. This is the form a plus b times a minus b, which becomes just a squared minus b squared. So this left-hand side shakes down to 1 minus sine squared. And ooh, there's a cosine squared on the other side. So let's add sine squared to both sides. And now we have 1 equals sine squared plus cosine squared. Sine squared plus cosine squared is 1. Okay? This does it. This locks it in. So again, remember that I'm going to scroll back up to the top. We followed these equivalences from the original opening expression is equivalent to the next one, which is equivalent to the next one, which is equivalent to the next one, and so on. And we boil it down to the fact that the original identity is equivalent to the statement that 1 equals 1. Okay, well, 1 is equal to 1. This is a true statement. We can follow these equivalencies uphill. We could have started with 1 equals 1 and then turned it into 1 equals sine squared plus cosine squared, and then turned it into the step above it and turned that through some factoring into the step above it. So we could have started with 1 equals 1 and evolved that uphill back to the original identity. And so that locks in 2 equivalent statements. They both have to be true since they're equivalent, and that demonstrates that the original expression is valid, because so is this one, so is this one, so is this one, all the way downhill to the one that's obviously correct and valid, and then that's like a big rubber band. It's all attached. Okay, so those are the 2 main strategies that are going to get you through the majority of proving trig identities. Is either, if it's complicated equals simple, try to just evolve the complicated side through some individual steps to get to the equal side, or the simple side, or carry over the whole expression through revision after revision. Either one of them can do the trick. Some might be more strategic than others, but that's usually going to get it done for you. Don't always think that you have to start with one side and get it to the other side. You can do like this second example and evolve the whole thing. And I don't know how many more times I can repeat the same thing, so I'm just going to shut up now.